In previous videos, when we talked about entropy and when we talked about equilibrium, we were referring to systems that were essentially isolated. They weren't able to exchange energy or entropy with their surroundings. What I want to consider now are systems in which they can share their energy and entropy with either their surroundings or some other sort of system, right? And so when it came to these isolated systems, we saw that they reached equilibrium when they were able to maximize their entropy. What we're going to consider now is the case of two isolated systems that are initially at equilibrium in their isolated states, and then they're put into thermal contact with one another. So let's now consider a case where isolated systems which have initial internal energies designated as U1 and U2 are put into thermal contact. And so the picture you should have in your head is of this. Okay? So what we're going to have is we're going to have two systems that are initially isolated from each other and the surroundings. And these systems are going to have some sort of internal energy, volume, and number of molecules associated with them. And consequently, there's going to be some sort of entropy associated with each of the two systems as well. At some point, the two systems are put together such that they're able to exchange energy with one another. So they're able to exchange energy with one another, but the total energy of the system, of the two combined systems, is conserved. And so in order to analyze this sort of system, what we're going to do is we're going to consider the composite system as just one sort of super system. So let's consider composite system as one super system. Okay? Alright, and so the two systems are able to exchange energy with one another, but the molecules in each system are not able to mix with one another. Right? Imagine there's some sort of partition that prevents mixing of the molecules. Okay? So because the molecules in 1 and 2 cannot mix, what that means is that the microstates for each of the subsystems are going to be independent. Okay? And so because the microstates are independent, that means the overall number of microstates, omega t, is just going to be the product of the number of microstates in system 1 and the number of microstates in system 2. Right? If we take the natural log of the total omega and multiply by Kb, that will give us the total entropy of the system. Right? And because omega t is equal to the product of omega 1 and omega 2, based on our log rules, we could split these out. ln omega 1 plus Kb ln omega 2. Right? And by definition, each of these things is an entropy. And so the total entropy of the composite system is just equal to the entropy of subsystem 1 and subsystem 2. Okay? Alright, and so that makes sense. The total entropy is just the sum of the two entropies of the subsystems. Now, when it comes to the energy, we could have energy going from 1 to 2, or even from 2 to 1, right? Both possibilities are allowed. And so as a result, if we think about it, the internal energy of system 1 and internal energy of system 2, those are going to constantly change, or they're going to constantly fluctuate due to energy transfer. Okay? But due to the conservation of energy, the total energy of the composite system has to be equal to U1 plus U2, right? So this cannot change, but these can. Okay? And so if we, based on this, we could rewrite that the internal energy of system 2 is just going to be the total internal energy minus U1. All right? And so with this sort of relationship in hand, what I'm going to do is I'm going to rewrite the microstate formulas in terms of just U1 only. So the total number of microstates is equal to the microstates in system 1, which is just a function of U1, times the number of microstates in system 2, which I'll say is a function of UT minus U1, where UT, remember, is a constant.